800,000 compute hours in a weekend, transforming regulatory pathways. That is the power and promise of HPC and AI. That is the power that the breakthroughs of tomorrow require. Now, more than ever, advancement relies on scientists and high-performance computing systems working together. As the needs for advanced simulation and modeling grows, so too do the demands on the system. One of the places this is most evident and important is in the work the Department of Energy is doing. Here to talk about how Azure's HPC platforms are being used by scientists to safely harness nuclear power and make batteries cleaner and more efficient is John Turner. He is the Computation Engineering Program Director at Oak Ridge National Laboratory. John has graciously agreed to answer questions today, so ask away in the chat. Over to you, John.
Thanks so much, and thanks to the organizers for inviting me to speak. Yes, I sit on the computational side of Oak Ridge, and I'll talk about a little bit about the national labs. I think you're pretty aware of them already. But why are we interested in cloud HPC, and a couple of demonstration cases that we selected and then implemented on Azure HPC. So first of all, I wanted to make sure I say thanks to the Microsoft Azure team, really essential in getting things set up for us, and then the Oak Ridge staff who contributed to these projects and actually executed the programs on Azure HPC. So I think you're probably fairly aware of the National Laboratory System. There are 17 of them. Oak Ridge National Laboratory, where I work, is in East Tennessee. And there are other, we're one of the Office of Science laboratories, and there are other laboratories that have parent organizations within the Department of Energy aligned with either national security missions or renewable energy or nuclear power. So Oak Ridge began with the Manhattan Project, like some of the other labs like Los Alamos and Livermore. We've evolved from there to become a leading science and technology laboratory with a focus that's fairly diverse across the science, from astrophysics to material processes to neutron science to energy systems, biological systems, and of course, high-performance computing and data analytics really underpins many of these efforts across the spectrum. You know, the Department of Energy continues to deploy some of the largest platforms and the computational platforms in the world. Two of the most recent ones are at Oak Ridge and Lawrence Livermore. They're sister machines known as Summit and Sierra. And I'll point out that the Office of Science facilities, like at Oak Ridge, Argonne, and Lawrence Berkeley, those are actually user facilities that provide allocations to the broad community without cost. There are some requirements through multiple programs. So I'll touch on that a little bit more later. As I mentioned, Summit and Sierra are kind of sister platforms, and they really are representative of current and future HPC systems. They have very high-speed interconnects, high-performance file systems, powerful CPUs, and then accelerators to provide most of the compute power. So they're very good at the traditional HPC modeling and simulation activities, data analytics. One thing that's happened recently is the addition of silicon on the accelerators, in particular, in this case, NVIDIA GPUs, that make them exceptional for artificial intelligence and machine learning. And so they really point the way to the future. That really came into a play with Summit and Sierra. Over the next few years, DOE is going to be deploying exascale systems at Oak Ridge, Argonne, and Lawrence Livermore. And these will be rolling out. And so to help prepare for those systems, which have some different architectural aspects to them, the Exascale Computing Project was started in 2016, which is a 7-year, almost $2 billion project, really to accelerate the hardware. So we're working with the vendors that make the CPUs, the systems, and the interconnects, the fundamental software that makes these machines operate, and maybe from my perspective, one of the most important aspects is the application space. So doing research in traditional areas like stockpile stewardship on the national security side, to astrophysics, to fundamental material science and chemistry. I'm going to touch on a couple of them that we chose as demonstration projects that are connected to ECP, one on wind turbine efficiency, and one on additive manufacturing of metal parts. Before I leave ECP, I want to mention that there is an industry council where we have executives of U.S. companies that really see HPC as vital to their success, providing advice and feedback to the ECP director. And we meet with them on a regular basis to inform them of where we're headed, progress we've made, and we've had a number of spin-off collaborations using the technologies that are being developed within ECP. So if we're fielding these big platforms, why is DOE interested in cloud computing? Why did I take on this effort to really investigate it for our use? And it really falls down to two things. One is support for our R&D programs. Now, currently, the allocation requests are exceeding the available resources by a factor of 3 to 4, and that's across the DOE, not just at Oak Ridge, but at Argonne and Berkeley and Idaho and NREL. So just supporting our basic R&D mission at DOE is one of the needs. The other one is deployment of our capabilities and partnerships, particularly with industry. So there are some programs like HPC for Energy Innovation, started in 2015 with the Advanced Manufacturing Office, working with industry to extend our capabilities and work with industry on attacking problems. And then the calls for projects out of offices like EERE are increasingly pointing to HPC and data AI as ways to achieve their mission. So just looking at one example, there was a project with between Oak Ridge and Rolls-Royce, looking at the manufacture of ceramic matrix composites and how you can optimize the weave to get optimal flow within and reaction to get rapid manufacturing, but also good quality parts at the end. So we extended a capability. We ran some simulations to help Rolls-Royce understand the problem. But what happens after the project is complete? How can Rolls-Royce integrate that capability into their design optimization workflow? Well, they really kind of have two choices. One is extend their in-house or on-prem resources, or look at maybe a cloud option. So we wanted to investigate how viable is that option for something like this. And OLCF, which is the leadership computing facility at Oak Ridge, has had a vibrant industrial partnerships program for a decade and a half now, working with tons of companies across the spectrum of U.S. industry. And we provide them help either addressing problems, assessing the return on investment. Again, it's the same kind of story. What happens after these projects complete? They can't use Summit and Sierra, these machines on an ongoing basis for production. So they're faced with the same kind of question. So we identified 3 problems that are relevant to the DOE mission: solidification, CFD, and electrochemical energy storage. And I'll talk a little bit very quickly about these. So we took codes that were already in existence, identified good problems, and ran them ported them to Azure HPC, and then ran them. So metal additive manufacturing, it's really transforming manufacturing. And I'm not talking here about polymers that you see in the kind of desktop devices, but we can actually 3D print metals, titanium, stainless steel, nickel-based superalloys. And one of the challenges is they can present some unfamiliar microstructures that sometimes don't behave so well. but there's an enormous parameter space for optimization. So fundamental to all of this is solidification. So at a core level, to understand and ultimately control metal additive manufacturing, you have to understand solidification. So we took a fairly basic 2D binary alloy problem that we understand very well, took one of the codes that we're developing within the exascale computing project, and ported it over to Azure and ran it. So this was a fairly modest problem. We can do 3D as well. We're just showing the 2D result here. Used 80 cores, wall clock time of 7 hours, and it's really, the performance is similar to what we have on-prem. The second problem the application we chose was wind farms. A massive range of scales here, 8 orders of magnitude at least, from the blades of the turbine up to the mesoscale type weather effects. And we're pretty good at this point in doing a single turbine blade, but the exascale project on wind energy is really looking at the problem of the interacting wakes. How do these wakes evolve and interact downstream? And so how can we better optimize the placement of wind turbines on a farm? And it can make a huge difference for both the lifetime of the turbines and the efficiency of the wind farm itself. So again, for this demonstration, we just selected a single turbine problem. This is the 5 megawatt rotor at NREL. Very well understood, very well instrumented. So it's a problem that's been run a lot of times over time. So we understand what the results should look like. We ported it over to Azure. This time, it's a larger problem. We ran on 1,000 cores, about 18 and a half hours for two rotor revolutions. And again, overcoming some challenges in containers and permissions. Ultimately, we were able to do the simulation and get the results. And performance is really, again, similar to what we see in-house. So that's great. The third problem is one that Cheryl actually touched on in the very opening session, the importance of energy storage. So this hits across DOE mission space from, not just, the most visible may be in vehicles like Teslas, but really it hits grid storage. And so recently there was a new initiative across DOE called the Energy Storage Grand Challenge, really looking at how do we accelerate and improve the lithium-ion batteries and other options for energy storage. So we've done work in this area. So we took the code that we've used for this. And in this case, whereas the first two examples, we were really rerunning problems that we had done in the past. In this case, really, we had actually never done a problem of this scale. So we took a battery pack, 30 kilowatt hour battery pack with 40 modules, multiple pouches within each module. We've meshed it up down within the pouch level. So this is an enormous, very large problem, 100 million degrees of freedom. Did a discharge for 100 seconds. And so this is the largest problem we've done on Azure so far. Again, it's not huge compared to Summit, but we want to get our hands on the challenges and how does it work. So this was almost 3,000 cores, and it scaled very well, 90% efficiency up to those almost 3,000 cores. And again, it's a problem we had not done before, so very, very large. I'll close with just a couple of words on where we see things going. And this is a term that came up in the fireside chat at the beginning as well. Edge computing, we're seeing a move within Oak Ridge to needing more capability at the instruments that are distributed across our campus. So the high flux isotope reactor, the spallation neutron source, these are big facilities, generate a lot of data. And so we see a move over the next few decades, really from purely centrally located compute facility resources to really a more distributed, having more capability out at the edge where these instruments are generating data. So it's really almost like a cloud type environment, even within our own institution. So with that, I'll close, and I'll just thank the teams again, both at Microsoft and at Oak Ridge. Even though we're deploying these large systems, we're the needs are accelerating, and we still need additional capability, and they're great for deploying our capability to our partners. We selected these 3 cases, which are representative and relevant to the DOE mission, implemented them, and we're pretty happy with how that went. There's some concerns regarding spinning up and spinning down the VMs, but really, ultimately, the performance is comparable to on-prem. Next step, we really need to do a detailed cost analysis. We haven't quite done that because it is a complex landscape. But thank you, and I'll take some questions if there are any, if we've got time.
Thanks, John. The first question, based on your experience, what are the right types of projects to take to the cloud?
So I would say ones where we're, hang on, I'm getting a little here. Let's see. Okay. Ones where you may not need a giant, single machine like Summit. Really that's the only place you're going to get the capability for a very large problem or very, very high throughput. But if you're talking more about a production, design optimization, or explore some parameter space, and you're not so concerned about maybe real time, at least from a R&D standpoint, it's very well suited for something like cloud.
Great. Thanks, John. What drives your use of cloud? Needing resources you can't get at Oak Ridge or collaborating with commercial partners?
Sorry, can you repeat the first part?
Sure. What drives your use of cloud? Needing resources you can't get at Oak Ridge or collaborating with commercial partners?
It's really both of those. I mean, I think, yeah. So one is, especially on the applied side of DOE, there's a need for additional capability. And whereas some of the science programs, astrophysics, climate research, fundamental chemistry and materials, those are really well suited for the very large machines. But some of the more engineering or design type challenges will fit very well on the cloud resources. And it helps alleviate. It's like a relief valve for the large systems that we have.
Thanks, John, for being with us today.
Thank you.